And as concerning our today's program, I'm going to finish with the discussion of the covariant quantization approach to electromagnetic field, and then to start a new relatively large theme, which is called the S matrix of quantum field in quantum field theory. Now, what remains to discuss concerning the covariant quantization approach is the construction of the propagator of electromagnetic field in this approach. And the definition of the Feynman propagator for electromagnetic potential is the same as you might expect from the discussion of the propagator for the Klein-Gordon field or for the Dirac field. So essentially, it is defined in a similar way as a vacuum expectation value of the time-ordered product of components of electromagnetic field taken at different space-time points. So it's a standard definition of the Feynman propagator. All what you need to do now is to take an expansion of electromagnetic field, which we have obtained in the previous lectures, in terms of oscillators, plug this expression in, and compute the time-ordered product, reduce it essentially to their normal ordered product of creation annihilation operators, and get the result. Since A mu is given by relatively complicated expression, this computation is technically involved, and I will not be doing it here explicitly, but it's written down in my lecture notes, so you can have a look there how this is technically done, how the derivation of this propagator is technically done. Let me just quote the result. So the result is relatively simple, and it's given by the following expression. If I restore all the units, then the propagator is proportional to h bar c, and this quantity h bar c has a dimension, physical dimension of square of electric charge, and then the four-dimensional integral of exponential minus I k x minus I k squared plus I epsilon, and in the brackets you have eta mu minus lambda minus 1 divided by lambda k mu k nu divided by k squared plus I epsilon. This is how this propagator looks like. And I have to point out that in deriving this expression, the contribution of all polarization modes, including the longitudinal and time-like photons, has been taken into account. So to this propagator, once again, everything contributes. So in addition to transverse modes, also longitudinal and the time-like photons do contribute. That's also, I mean, this expression also shows that if you would like to write down the propagator in the momentum space, all what you do, you take inverse Fourier transform, and in the momentum space, delta mu nu on momentum k will be written as h bar c minus I divided by k squared plus I epsilon, eta mu nu minus lambda minus 1, lambda minus 1 divided by lambda, k mu, k nu divided by k squared plus I epsilon. So all lambda dependence comes out proportional to this product k mu, k nu. Okay, so this lambda dependence concentrates, I mean, it comes out with this product k mu by k nu. And sometimes it is very convenient to fix lambda to a certain value. So fix lambda and two choices are used most often. And they historically are called gauges. So fixed lambda historically was called to fix a gauge. And perhaps only the second choice, which I will show you now, can really justify this name, gauge fixing. Now, the first choice of lambda is corresponds to what is called Feynman gauge. Feynman gauge. Oops. And it corresponds to putting lambda to be equal to 1. So this is a choice which makes the corresponding propagator very simple, and it is then given by, in momentum space, simply by minus I divided by k squared plus I epsilon eta mu. So essentially, you see that this is concerning the momentum dependence. This is the same propagator as for the scalar field, and all tensorial properties of delta mu are just concentrated, are just rendered by the Minkowski metric eta mu. So that's the simplest propagator you can imagine. The other choice corresponds to the so-called Landau gauge. Landau gauge, where people are taking lambda to be equal to infinity. And in fact, this choice, lambda is equal to infinity, that corresponds to enforcing the Lorentz gauge condition. So that corresponds to somehow enforcing the Lorentz gauge, d mu a mu equals to 0. This is because, as you remember, in the original Lagrangian, we have a contribution given by lambda multiplied by d mu a mu squared. And that means that if you, for instance, compute energy, then in the limit lambda to infinity, this term contributes a very large amount to the energy, and in order to minimize the energy, enforces to impose the condition d mu a mu to be equal to 0. And so in this gauge, if you consider here this term and send lambda to infinity, you see then this propagator acquires the following form: h bar c minus I k squared plus I epsilon eta mu minus k mu divided by k squared plus I epsilon. This is what is called propagator in the Landau gauge. Now, this propagator has a property to be transverse in the four-dimensional sense. Namely, if you now take this expression, if you write it as a x-dependent propagator, so we integrate over d4k divided by 2 pi in the power 4. And if you now get it with derivative and sum up over index mu, then you discover that the result is 0. Well, you can see it, yes, minus ikx. Well, you can see it from here. So if you act with derivative, d over dx mu, then k mu gets down from the exponent. And then here k mu gives k squared. It's the same thing which is in the denominator. So they will cancel, and here k mu together with eta mu will produce for you k nu, and therefore these two terms cancel, being projected with k nu. And therefore, in this gauge, the propagator will satisfy this transversality condition in the four-dimensional sense. Now, concerning the gauge invariance, coming back to this issue of the gauge invariance, well, so far we have treated the field A mu as having 4 degrees of freedom. And as I said, all of them were taken into account in computing the propagator. Now, this is well-defined and unique propagator, well, provided we have used the above quantization procedure, which we have discussed in the last 2 lectures. Now, it turns out, however, that in quantum electrodynamics, the theory which we will consider a little bit later, the photon propagator always occurs in a specific combination. Namely, there are currents produced by Dirac spinors, Dirac fermions, describing electrons and positrons, propagator delta mu, and then another current J nu. So that's a typical contribution, say, to scattering matrix or to the correlation functions. And here J mu is a conserved current, which satisfies the conservation law, conservation condition, namely K mu J mu is equal to 0. And in this situation, you actually see that nothing prevents us from modifying the propagator. So I can take the propagator with fixed lambda, and I can change it by adding to it the terms of the type K mu chi nu plus chi nu K nu chi mu, where chi is an arbitrary chi mu, say, is an arbitrary function of K0 and 3-dimensional vector K. And it's not even necessary that this chi mu is a component of the 4 vector. It can really be arbitrary 4 functions parameterized by this index mu. So mu runs 0, 1, 2, 3, but it's not necessarily a Lorentz vector. That's because if you now change the propagator in this way, then you see that this expression J mu delta mu J nu will change for J mu delta mu J nu plus J mu K mu kappa nu J nu kappa chi nu J nu plus J mu multiplied with K nu J nu. And because of this equation here, you see, this is, by the way, what is called conservation law of the current or continuity equation. It has different names. And you already seen this equation in Maxwell theory, I'm sure. So this is in the classical Maxwell theory, it's called continuity equation, but it also holds in quantum theory as well. And so due to this continuity equation, this term is 0 and this term is 0 as well. And so you see this expression J mu d mu J nu is actually immune to this change of the propagator. You modify the propagator in this particular way, but the corresponding contributions to the elements of the scattering matrix or to correlation functions will not see this change at all. And this is, in a way, implementation and, if you wish, manifestation of the gauge invariance in quantum theory. Now, of course, to this statement to be fully true, the current J mu, as I said, must be conserved at the quantum level. And the equations describing its conservation in quantum theory is known as a word identity. So you get what is called word identity, which in a way, a signature of presence of symmetry at the quantum level. At the quantum level. In fact, this possibility to modify the propagator shows that the lambda-dependent part of the propagator decouples from correlation functions. Indeed, if you look at this expression here, you see that since the lambda-dependent part is proportional to k mu k nu, then multiplied with the current J mu, which is conserved due to this conservation equation, the lambda-dependent part will simply decouple. That also shows that the choice of the gauge, I mean, fixing lambda to a particular value, should not be important, because independently of what lambda is, there will be decoupling of the corresponding lambda-dependent term from the correlation functions and the matrix elements of the S matrix. Now, also, picking up a proper function chi allow you to transform the propagator from one gauge into the propagator in another gauge. For instance, if you take chi to be the following, you pick up chi 0 component to be equal I divided by k squared, k 0 divided by 2k vector squared, and you pick up chi I to be minus I over k squared, ki divided by 2k squared. So if you make this choice of the components of chi and modify the propagator according to this formula, the simple calculation shows that the case of lambda is equal to 1, which corresponds to Feynman propagator, transforms your propagator to the propagator which is called Coulomb propagator because it corresponds to fixing the Coulomb gauge. Coulomb propagator with components, with the following components. So this Coulomb propagator is the one which has component delta 0, 0, given by I divided by k squared. It has component delta 0 I, which is equal to 0. And finally, the component delta ij will be given by I divided by k squared, delta ij minus ki kj divided by k squared. That is what is called Coulomb propagator. And in the Coulomb propagator, this in the Coulomb gauge, this Coulomb propagator satisfies the transversality condition, but in the three-dimensional sense. So delta ij kj is equal to 0, and delta 0j kj is equal to 0 as well. So you see this transformation here, which produce no effect on physical quantities, allows you to move from one gauge to another, which is very convenient. So as you see, I reproduce for you here the Coulomb propagator without doing any actual computation in the Coulomb gauge, where divergence of A is equal to 0. So it's very convenient. It's very convenient to have this fact in mind. So typically in modern calculations, people use these two propagators, which I mentioned, and the most popular is, of course, the propagator corresponding to the Feynman gauge, because in this gauge, the propagator is especially simple. Especially simple. I mean, k-dependent path is the same as for the case of a scalar field in the case of the Klein-Gordon field. Okay, any questions here? I think I finished with the sim covariant quantization. And the most important outcome, of course, is that we have seen how to construct the Hilbert space of states by using the Gupta-Bleuler formalism. And we also understood, at least at the level of an idea, how to construct the Feynman, or how to construct the propagator for electromagnetic field, and what is an effect of these lambda dependent terms, how we can go from one gauge to another by using the freedom in the redefinition, in the definition of the propagator, due to the presence of the word identity, namely the conservation of the electron-positron current. Okay.
First, I have a question.
Sure. Go ahead.
So we know that the constraint can be complete or incomplete, but for the propagator, it doesn't matter whether the constraint is complete or not, right?
Yes, for the propagator, we see that this presence of gauge invariance, on the one hand, it leads to the conservation of electron-positron current, and this in turn implies that actually the different gauges which you might attribute to the presence of this term in the propagator, which depends on lambda, is not important, because you can move from one gauge to another, and this makes, in a sense, all these different gauge choices to be equivalent. So it means that in practical computations, which you would like, if you would like to compute the physically relevant quantity in such a theory as electrodynamics, you can use any of the propagators you like. In principle, you can even keep lambda to be arbitrary, just not to fix it. But then at the end of the evaluation of the matrix element of this matrix or correlation function, you should see explicitly that this lambda dependence completely decouple. That would mean that your computation is done correctly. And in some computations, people prefer to keep lambda because it provides an independent check that your computation is done correctly. But we see a certain reason for that. We see a reason for that. The reason is the current conservation, which allows to modify the propagator in this particular way, which actually shows that lambda-dependent terms are not important. They drop out. They will drop out. Okay?
Okay, thank you.
Good. So now we are coming to the discussion of scattering theory. And so I prefer to start from a bit simplified picture of scattering in quantum mechanics, because if you understand how the scattering theory works in quantum mechanics, it is not so difficult to understand how it will work also in quantum field theory. And therefore, we start from quantum mechanical scattering, and then develop a certain formalism, and then see how this will be generalized to the case of quantum field theory. So, in quantum mechanics, we start from the time-dependent Schrödinger equation. So if you want to describe scattering, the first thing to start is a time-dependent Schrödinger equation, which you know very well how it's written down. So I h bar d over dt, the wave function psi on t, which I will write as a vector in the Hilbert space, equals to the Hamiltonian h, which is an operator. In quantum mechanics, it's called Schrödinger operator, acting on psi on t. So this is our Schrödinger equation. And I assume that I'm working in the picture where the operators do not depend on time, while the time dependence is on the wave function, So then that's explicitly indicated in this formula by writing psi as a function of time. Now, this equation then can be elementary solved because h is time independent, and so solution you know very well. So psi on t is given then by operator u on t acting on psi on t, where u on t is a unitary operator explicitly given by minus I exponential minus I h bar, the Hamiltonian multiplied by time multiplied by psi, where psi now is same as psi is by definition the same as psi on zero, psi at 0 moment of time, is any proper vector in the Hilbert space H. And E is called evolution operator, is what is called evolution operator. Now, proper vector, the word proper means that this vector is a vector in the Hilbert space which has a finite norm. So proper means finite norm. Finite norm. And you know, so in quantum mechanics, physically say in the, if you realize quantum mechanics in the Hilbert space L2 of square integrable functions, then such a proper vector will be described by a wave packet, free wave packet. Far away from scattering center, this vector describes what we call free wave packet. So in quantum mechanics, particles, if you wish, due to this de Broglie particle wave duality, will be described by a wave packet. And so then wave packet undergoes an evolution, which is described by this vector psi on t. Now, following back in time, if I go back in time, if I sort of consider my film describing the scattering of psi back in time, then this is a wave packet that is localized far away from the scattering center. And since it's very far away from a scattering center as time goes to minus infinity, it should tend to the free wave packet. And the free wave packet means that the motion of a free particle is described by a free evolution operator, which I denote as u0 on t. And this should be given by exponential minus I divided by h bar h0t, where h0 is simply the Hamiltonian of a free particle, p squared by divided to m, and where m is the mass of a particle. And of course, in this picture, I assume that the Hamiltonian h admits a separation on a free part and the part which describes, which is a potential, describing the interaction of this particle with a scattering center.
This is Schrödinger picture, right?
That's a Schrödinger picture where the wave function is time dependent and the operators are time independent. And you are right, in the quantum mechanics, we can adopt two different pictures for the description of quantum mechanics. One of them is Schrödinger, another is Heisenberg. In the Heisenberg picture, the operators depend on time, the wave function is time independent. But here we are working with Schrödinger equation. We naturally use Schrödinger picture where operators are time independent and the wave function is time dependent. That's right. Now, in quantum theory, it is assumed that the Hamiltonian H0 has the same spectrum as H. It means in particular that masses which appear, I mean, this mass, for instance, in the simplest situation where we have just a single particle, it means that mass appearing in this H0 must be the physical mass that is measured in experiments. And this mass, as we will see later on, might not coincide with the bare mass entering the expression for H. And this is due to the effects which are related to the so-called renormalization. We will come back to this and it will become more clear what I mean by this. Now, the difference between the bare mass and the actual mass is actually, in the scattering picture, is attributed to this potential V on X. So in other words, in H0, you have not a bare mass, which originally put in the Lagrangian, but is an actual mass of a particle which you measure in experiment. Now, as I said, we expect then when t goes to minus infinity, what happens is this state u on t psi tends to u0 on t, acting on some state which I called psi in, for some vector psi in the Hilbert space. And analogously, after the collision of a particle with a scattering center, when t goes to plus infinity, you might expect that u on t acting on psi, when t goes to plus infinity, again tends to the free evolution operator acting on some other state which is called psi out. For some vector psi out also belonging to the Hilbert space. Therefore, the asymptotes of quantum scattering problem are labeled by two vectors, psi in and psi out. In fact, as in the classical case, one should not expect that every orbit, this thing is called orbit, this orbit or trajectory of a state, but now not in the physical space, but in the Hilbert space. We cannot expect, just from experience from classical theory, that any such orbit will have asymptotes, because there might be bound states. For instance, imagine that you have some scattering center and there is an attraction, and so you shoot the particle, it goes to the scattering center, and then somehow it goes on a stationary orbit around scattering center, and so it becomes a bound state, and there is no out asymptote because your particle now was captured by scattering center, so nothing gets out. You shoot a bullet on a target, but nothing comes out for an observer at a distance. Bullet disappeared because it becomes a bound state. So we cannot expect that any orbit has an asymptote because of the presence of the bound states. But what you could expect, so let me say that the whole Hilbert space, if I denote the Hilbert space like this, it splits into two parts. One part corresponds to scattering states, which have asymptotes in and out, and the bound states. Bound states. That those which do not possess either in or out asymptotes. And the assumption which one takes in scattering theory is that there is no any other states in the Hilbert space. So Hilbert space consists either from bound states or scattering states. From the point of view of this orbit U on T acting on psi. So psi is, to have a scattering psi must be from the part of the Hilbert space which correspond to scattering states. However, one can show that for any psi in from the Hilbert space, there is such vector psi, that the asymptotic conditions, which I denote by star, are hold. Psi in and psi out in H, such as there exists psi such that star holds. And here such that second equation in star holds. In other words, every vector in H, does represent the asymptote of some actual orbit. And this result, this is a theorem, this theorem or this result is known in scattering theory, as the so-called asymptotic condition. Asymptotic condition. Asymptotic condition. So asymptotic condition guarantees that any vector psi in the Hilbert space is in fact the in asymptote of some actual orbit U on T acting on psi. Maybe I should draw the picture which somehow appeals to a geometric intuition what's happening. So imagine that somewhere here we have a scattering center. And imagine that we send on this scattering center the particle from infinity. So at t goes to minus infinity, we have our particle, and which moves towards the scattering center, towards the target. And let's, for simplicity, assume that the potential is reflective. So our particle will be reflected and will have out asymptote. Then the trajectory of this particle will be something like this. It comes from minus infinity, it moves close to the scattering center, and then it goes out. And then you see that if the scattering center would absent, there will be no scattering center. I should maybe use another color here. If there would be no scattering at all, so scattering center would be absent, then our wave packet will just travel without scattering. And so this then state, in fact, I would call, so the potential is somewhere here, concentrated somewhere here. This state I would call psi in. If I denote this, if this green line denotes the Hilbert space H, then at a time equals to 0, this is where my states are taken from. Time is equal to 0, Hilbert space H. The state at t is equal to 0 would be psi in. Then there is a out asymptotics. When I go very far away in time, then there will be say some, maybe I draw it a little bit further by red, something like this. And then if you draw the out asymptote, then it will go somehow, somehow like this. Maybe another color. Yeah, let me take another color. It will go something like this. And it will have intersection with a Hilbert space H, which I denote psi out. So psi in and psi out, these are the states in H which correspond to in asymptote, and out asymptote. And the actual scattering state is somewhere here. This is where your trajectory intersects the green line. It gives you the actual evolution from psi in to psi. And therefore, you see in H, you have built three vectors. At t is equal to 0, you have three important vectors. Psi, which describes the scattering state, the state which you are going to scatter with the evolution operator defined by full Hamiltonian. And you get two states, psi in and psi out, which will travel either to minus infinity or to plus infinity under the action of free evolution operator defined by free Hamiltonian. And this psi in and psi out represents in and out asymptotes. Now, the fact that you have asymptotic condition satisfied means that, let me see, means the following. It means that there is a limit which allows you to define the vector psi. So we said psi on t goes to psi 0, u on t on psi goes to u on 0 on t on psi in. When t goes to minus infinity. So from here, if you multiply this relation by u dagger on t and take a limit t to minus infinity, you find the relation between psi and psi in. So it is given by lim t goes to minus infinity, u dagger on t, u0 on t, acting on psi in. So in other words, if you want to detect psi, which corresponds to a chosen vector psi in the Hilbert space, then you have to compute this limit. And in fact, what you have here is an operator acting on psi in, and this operator is historically denoted by omega plus, acting on psi in, and this operator is called Mueller operator. Mueller operator. Analogously, our state psi at t is equal to 0 will evolve into out asymptote labeled by state psi out, and this is given by similar expression, but this time limit is taken for t going to plus infinity, u dagger on t, u0 on t, psi out. Psi out. And this is denoted as omega minus acting on psi out. That's a bit inconsistent notation because t going to minus infinity is represented by omega plus. It would be natural to call it omega minus, but I cannot do anything about this. It's somehow historical notation for Mueller operators, and I decided just to keep it because this is how it's written in the books. This is how it's encoded in the books by now. So omega plus and omega minus are Mueller operators which describe the relation of asymptotes psi in and psi out, which are proper vectors in the Hilbert space, to an actual scattering state psi, which is a state in the Hilbert space at t equals to 0, at the 0 moment of time. Now, these operators, omega plus and omega minus, are very interesting. In fact, as you see that they are given by limits of the products of two unitary operators. And for this reason, these operators preserve the norm of any states in the Hilbert space H. So omega plus minus, so statement is that omega plus minus preserve the norm in H. For this reason, these operators omega plus minus are called isometric. Isometric operators. They preserve the norm in the Hilbert space. And the preservation of the norm means that omega plus dagger, or plus minus dagger, omega plus minus is equal to 1. But in functional analysis, it is actually proved that the limit, such operator limits of unitary operators might not be unitary. So they are isomorphic, but it's not necessarily unitary. So the inverse relation where omega plus minus on the left-hand side and omega plus minus dagger on the right side might not necessarily be equal to 1. Would it be 1, then it's an operator which we call unitary. And as you know, in a finite dimensional case, from this relation here, you can always prove that the opposite relation, omega plus minus dagger, is also equal to 1. That would be the case only if your Hilbert space is finite dimensional. In the infinite dimensional Hilbert space, this is not necessarily so. So, meaning that the operator might be isometric, but not unitary. And so this is what is called here isometric, but the opposite relation where omega dagger is not equal to 1 means that operator is not unitary. And the reason for these operators, omega plus minus, not to be unitary is more or less clear. So what happens is that omega plus and omega minus, what they do, they map, they are mappings from the Hilbert space H into a part of Hilbert space which correspond to scattering states. Let's denote, say, scattering states, part of the Hilbert space which correspond to scattering states, like for instance, J. So this is a subspace in H corresponding to scattering states. Subspace of scattering states. And as we said, according to asymptotic condition, the full Hilbert space H is divided with respect to scattering states into two parts, the one which contains indeed scattering states and the other one which contains the bound states. And so Mueller operators map isometrically any state from H into a part of the Hilbert space which correspond to scattering states. So in other words, in mathematical language, omega plus minus are isometric, but these maps are not surjective. They are not the omega plus minus do not cover the whole Hilbert space, but only a part of it. This is possible because we are in the infinite dimensional situation. H is infinite dimensional, and the subspace of scattering states is also infinite dimensional. And it is possible to have an isometric in the infinite dimensional situation. It's possible to isometrically map the full Hilbert space on its infinite dimensional subspace. Actually, one example of this of such an operator, which is isometric, but which is not unitary, you know very well. If you consider just harmonic oscillator, then you know when you quantize it, you get operators A and A dagger, right? So usual harmonic oscillator. And then you start to construct states by acting on the vacuum state 0 with creation operators. So acting on vacuum with one A dagger creates a state 1 with one particle. Then if you take a state with one particle and again act with a dagger, you create a state with two particles, and so on. And so on to infinity. But you see, by a dagger, you can never create a state corresponding to the vacuum itself. So vacuum itself is missed, although this map by a dagger is isometric, because if you take any state created by a dagger, the norm of this state, the norm squared of this state, is, what is this? This is, this will be, say, vacuum A in the power n, A dagger in the power n acting on a vacuum. The commutation relation of A and A dagger is 1. If I put h bar equals to 1, and then what you get here is 1. So the operator A dagger is isometric, right? Any state n has a unit norm. But this operator is not unitary because it does not provide a one-to-one mapping of H into H. It misses this state here. And so the inverse of A dagger does not exist in a strict sense because it's not defined on the vacuum itself, right? Inverse of A dagger. Inverse of A dagger exists only if I consider part of the Hilbert space, well, infinite dimensional part, which is built up as 1, 2, and 3, and so on. But the vacuum itself misses the inverse of A dagger. So A dagger is isometric, but it's not unitary. And so such situation holds because you are considering here an infinite dimensional space. In the finite dimensional space, everything is simple. So if you have isometric operator, a dega, omega dega is equal to 1, well, then you say, okay, you take determinant of the left-hand side, determinant of the right-hand side, from where you find out that determinant of omega is not equal to 0, therefore it's an invertible operator. And so from here, multiplying by omega minus 1 from the left, you get that omega dega is omega minus 1. So omega minus 1 is important that it exists on the whole Hilbert space. And then you multiply it by omega from the right, from where you conclude that omega dega omega is equal to 1. And so your operator is unitary. From this condition follows, right? In the finite dimensional case. In the finite dim case. In the infinite dimensional case, this might not be so, as I said, that because omega dega has no inverse, and I cannot repeat this simple argument anymore. Okay. Now let's assume that our scattering state psi has both in and out asymptotes. That means that in the one case, it is represented, say, by omega plus acting on psi in, and on the other hand, it can be represented as omega minus acting on psi out. From where, because omega plus dega, omega plus is equal to 1, no, the same as for minus, you can find out the relation between psi out and psi in. For instance, acting on omega minus dega on both sides of this relation here, you get omega minus dega omega plus psi in is equal to omega minus dega omega minus psi out. So this is 1. And so you get the relation between asymptotic data, between asymptotic vectors in the Hilbert space H, which is omega minus dega omega plus acting on psi in. And this operator S, denoted by S, this combination omega minus dega omega plus, which is a map, as you see, from Hilbert space H to H. You see psi in H and psi out also in H. This map, or this operator, S, is called scattering operator. Scattering operator. And colloquially speaking, with some abuse of language, is called S matrix. This is a well-defined operator which acts on the Hilbert space of the theory and maps it to the Hilbert space of the theory. And this operator, this time, this S is unitary. That is very important. So S dega S is equal to S dega is equal to 1. So S matrix is a unitary operator. A scattering operator is unitary operator. Now, since in practice only asymptotic free motion is observed, so our observer, if you wish, is sitting somewhere either here, there is our eye observing this free motion, or our detector is here, and another detector is somewhere at asymptotic infinity. So here is our observer. So when in practice only free motion is observed, so that means that we can fix out state and we can set up in state. That means that operator S contains all information of experimental interest. That's why this notion of S matrix is very important. So that contains, all info of experimental interest. And that's why this object is very important object, even, I mean, not only for theoreticians, but also for experimentalists. It's an object of primary importance. In general, as we said, the Hilbert space splits into orthogonal sum of bound states and the scattering states. And the operator omega plus, it takes Hilbert space into space of scattering states, while omega plus dagger acts in an opposite way. So, and omega minus dagger, we are interested in omega minus dagger, it takes other way around. It is defined on the space of scattering states, and it sends scattering states into the H back. And that explains why S actually acts from H to H. So omega plus sends it from H to scattering states, and omega minus dagger sends back a scattering state into H. Okay, any questions here? Is it concept of S matrix is clear? It's built up from Mueller operators, and its introduction is based on the asymptotic condition that any state in the Hilbert space define a certain inner asymptote, and any space in the Hilbert space define a certain outer asymptote. Okay, if this is clear, we start to investigate further properties of the scattering matrix and Mueller operators. Now, first of all, let's consider the following construction. Take I over H bar, the full Hamiltonian H multiply with tau. Tau, it's like a time variable. And then omega plus minus, the Mueller operator. This we can write as follows: I over H bar H tau. Now we write Mueller operators as a lim t goes to minus plus infinity. U on t, which is I over H bar ht, and then free exponential since it's given by free Hamiltonian minus H bar h0 t. Then, since tau is finite, we can move it under the lim. We get lim t goes to minus to plus infinity, exponential I over H bar h t plus tau here. So I combine this exponent with this one. And what I will do here, I will write h0 t plus tau. So I add up tau here, but I need to compensate. And I write from the right-hand side minus, not minus, but plus I over H bar h0 tau. So I have not done anything. I've just add up and subtract the contribution of tau. And from this formula, you see actually that taking t to minus plus infinity is equivalent to taking t plus tau to plus or minus infinity, because tau is finite and t goes to minus to plus infinity, so shift t by tau plays no role. So actually, you see that you can write it in the following way. You still take the limit t plus tau going to minus plus infinity, so you can actually now remove tau and get exponential I h bar ht, exponential minus I h bar h0t, and this piece, which is a t independent, you can put it out of the limit. So you move this operator with the Hamiltonian h inside omega plus minus, and you get out the operator which is tau dependent, but it involves h0. And what is written down here is again nothing as omega plus minus exponential I h bar h0 tau. Now you differentiate this equality with respect to tau and put tau equals to 0. So when I differentiate this exponent here with respect to tau, I get h down. And when I put tau to 0, I will be just left with h. So the left-hand side gives h omega plus minus. And on the right-hand side, when I differentiate over tau, I will get h0 down. IH over h bar is 0 down. And then putting tau to 0 will leave me with omega plus minus h0. So this is a very important relation. It shows that the Hamiltonian h, full Hamiltonian h, going through omega plus minus produces the free Hamiltonian h0. Or if you wish, you can write it by using the isometric property of h0 in the following way. You can write it as omega plus dega h omega, actually plus minus omega plus minus dega h omega plus minus is equal to h0. And at first sight, this expression is very suspicious because it means that if operator omega plus minus is unitary, would be omega plus minus unitary, then this relation shows you that actually h and h0 should have the same spectrum, right? Because conjugation of the Hamiltonian by unitary operator cannot change the spectrum. This we know very well. Unitarity, imagine that H is a matrix and you perform on it a unitary transformation. A unitary transformation cannot change the eigenvalues. So at first sight, it looks suspicious. But on the other hand, we remember that omega plus minus are not unitary. They are unitary only if the Hilbert space has no bound states. Would it be the case that there are no bound states? Then indeed, omega plus minus would be unitary and spectra of h and h0 would be the same. Right. Now, from this relation here, from this relation here, we can conclude the following, that if I now take S matrix and commute the H0 through S, I can apply the following line of relations. So I write S as omega minus dega omega plus, with H0. Then H0 I commute through omega plus, and then it replaces by H omega plus, and then H commutes with omega minus dega, because this relation here also implies that omega plus minus dega omega plus minus, omega plus minus dega h is equal to h0 omega plus minus dega. Commuting h with one of these relations produce for you h0 omega minus dega omega plus, which is again S matrix. So this is H0S. In other words, this shows that S matrix as an operator on the Hilbert space commutes with the Hamiltonian H0. That's a very important fact in a scattering theory, which in fact reflects conservation of energy in the scattering process. Conservation of energy in the scattering process. Moreover, this time-independent states, psi in and psi out, you can think about them as being eigenstates of the free Hamiltonian, psi in and psi out, which is of course true because you can always consider them as being, you can diagonalize H0 and psi in, psi out can be taken as eigenstates with an eigenvalues which you call energy eigenvalues. And then you see also that if you take the full Hamiltonian H and apply it to a scattering, actual scattering state psi, then this can be written as follows. So this is H omega plus psi in. And we know that H through omega plus can be commuted, and then H will be replaced by H0. And if H0, if psi in is an eigen state of H0 with the energy E, then you get here energy omega plus psi in. But omega plus psi in is again equals to psi. And so you get a statement then that the scattering state psi is an eigenstate of the full Hamiltonian H with an eigenvalue given by E. Well, the same is, of course, for psi out. You can also represent psi via psi out and repeat this computation. Now, finally, from what we have learned about S matrix, so we said that S matrix is actually a combination, the following composition of omega plus and omega minus, like omega minus dega omega plus. And from here, you also see that if I substitute the definition on omega plus and omega minus, I will obtain an expression for the S matrix as double operator limit. T prime goes to plus infinity, lim T prime goes to minus infinity, exponential I over H bar H0 T prime prime, exponential minus I over H bar H T prime prime minus T prime, exponential minus I over H bar H0 T prime. So double operator limit. And this formula you may see in the books on quantum field theory. So sometimes people even start from this formula and say that this is the definition of S matrix. So essentially, you see it's an evolution operator driven by H from T prime to T double prime, or from, from T prime to T double prime, in the limit when T prime goes to minus infinity, T double prime goes to plus infinity. So the evolution from minus to plus infinity described as a full Hamiltonian, but then there are these how you can call it, you can call them, there are these cut-in factors which cut the corresponding evolution operator by making by the free evolution with the Hamiltonian H0. So to take into account the right asymptotic of the S matrix. Now this operator, as we said, it acts from the Hilbert space H into H. And therefore, if you consider, say, you pick up a basis in the Hilbert space made of, say, eigenstates of the Hamiltonian H0, so free Hamiltonian, say psi alpha, then you can compute the matrix elements of this S matrix with respect to this basis psi alpha. So this is what is called, say, beta here. I write typically beta here, alpha here. This is a matrix elements typically denoted by beta alpha. And so they describe transition from psi alpha to psi beta. And you might think about this psi alpha as a particle configuration in the initial asymptotic state, and this would be a particle configuration in the out state, in state, out state. And the rate of the reaction alpha goes to beta is proportional to the quantity S beta alpha minus delta alpha minus beta. So delta alpha minus beta describes the contribution which happens without scattering. So if there is no scattering, then beta configuration must be the same as alpha because no scattering occurred. And if you subtract this term from the S matrix and take a square of it, then this would be a rate of the reaction alpha goes to beta. Okay. Yeah. Yeah.
So from the scattering expression, we can also extract something called Dyson series, right?
We will come to that. We will come to that. So Dyson series will arise when we will be discussing indeed correlation functions. This is something which will come. Yes. Yes. So for the moment, I would like to find a practical way of evaluating the S matrix. Because this formula, which I'm writing here in the frame, is of course nice, but this is not so practical. This double operator limit, how I'm going to compute it actually. That is, of course, I mean, nice to write down, but how to compute? How to compute in practice? That's the first question. And the second question is how to relate this S matrix with something which you really observe in experiment or you measure in experiment. And what you measure in experiment is not necessarily, is not directly the S matrix, but rather it is a scattering amplitude and a cross section. And so there is a still a way to get out of the S matrix such a thing as a cross section. And this is something which is measured in experiment. So these are two questions we have to understand. The first thing is how to practically compute S matrix, relying on the knowledge of the interaction potential. And then second, how to relate this quantity to such a thing as cross section. And so concerning the first question, how to compute this S matrix in practice, we do the following. I mean, this expression, which is this double operator limit, suggests to introduce the following operator, I denoted by U, depending on 2 times T and T0. And this will be the same operator which stands in this double operator limit, except I will not take this limit. So I introduce the following operator. This, by definition, this operator is exponential I over h bar h0t, exponential minus I h bar h full Hamiltonian t minus t0, and then exponential minus I h bar h0t. So as much, if you return back to the definition, this is this operator taking t going to plus infinity and t0 being minus infinity. So then from this picture, it is clear that this operator U on T0 is an important object in scattering theory, and you have to study its properties. And this operator, indeed, it has a very nice property. It's called Markovian property, that if you multiply this operator at time t and t prime, and then multiply it with an operator on t prime and t double prime, then the result will be the operator evaluated at t and t double prime. So somehow this intermediate time t prime decouples from this product, and this is what is called Markovian property of this operator. It's also, in a sense, a group property. So multiplying 2 u's, you just get another u. Now, describing the time evolution of a state with the help of this operator u on tt0 is called the Dirac or interaction picture. So in this picture, the wave function u on t evolves according to the action of this operator t0 acting on a state taken at the moment t0. So what does this mean? So this is what is called Dirac or interaction picture. So this picture in quantum mechanics, so this is Dirac or another word, interaction picture. It's a picture, something in between the Heisenberg and Schrödinger picture. This is a picture most suitable for dealing with a scattering process. And that's what I'm going now to demonstrate for you, why this is the case. If you take this operator u on tt0 and differentiate it with respect to time t, so we take a partial derivative of du on tt0 over dt. What do we get? From the right-hand side, I need to differentiate first this exponent with respect to t. Then I over h bar h0 gets down. But since h0 commutes with the exponential of h0, I put then this h0 to the right. So I write it I over h bar h0t and then h0. Now I have to differentiate the second exponent over t. And this will produce for me minus I over h bar, h getting down. And so this produces the contribution where I put h to the left from its exponent. So this will be minus I h bar. Here there is something h0 t0. And then h t minus t0 exponential minus I h bar h0 t0. So the last exponent I am not touching because it depends on t0. It does not depend on t. Now, you see that this difference, H0 minus H, is nothing else as minus V, minus potential. Right? It's nothing else as minus potential. Potential is taken in the Schrödinger picture. So H0 and H are time independent. Therefore, V is also time independent. This is our initial setting. And therefore, you see that this result here I can write in the following form: minus I over H bar, exponential I H bar H0 T. Then I have the potential. And here I introduce minus I over H bar H0 T, and I compensate it by I H bar H0 T, exponential minus I H bar H T minus T0, exponential minus I H bar H0 T. And why I've done it? Because you see that what is standing here is again U on TT0. And therefore, what I have done, I have found the following interesting equation. If I put IH bar to the left-hand side, I get the following evolution equation for this operator. IH bar du on TT0 over dt is V on T, U on TT0, where V on T is an interesting quantity. That is my potential, time independent, and in other words, taken at T equals to 0, so operator in the Hilbert space at T is equal to 0, which undergoes an evolution with respect to free Hamiltonian. So this U on T is the potential which is obtained from the potential at T is equal to 0 by means of free evolution. That's very, very important. That's, I mean, the whole benefit of this construction is that now U on T evolves freely. In other words, with the help of the free Hamiltonian. And the operator itself, U on TT0, satisfies now this differential equation. This equation should be supplied with an initial condition if you want to think about how to solve it. Back, you see there is an initial condition. If I put in this expression T is equals to T0, then what I will get if I take T to be equal to T0, then T0 minus T0 here produce 0, so exponent in the middle turns into 1, and then these exponents which are standing at the left and the right end, they just annihilate each other and also give 1. So this operator is naturally defined in such a way that when times coincide, the operator becomes an identity. This operator becomes a unit operator. So U on T0, T0 is actually 1. That you can consider as an initial condition for this operator U. Now, this means that what you can do, you can now take this differential equation and integrate both sides of it from T0 up to T. And at first sight, it seems like you are doing something tautologic and not making much sense. But you will see that it makes a lot of sense. So here I have to put actually instead of T some other variable because I'm integrating over it. So let's put this integration variable to be tau. Let's call it tau, tau, d tau, from T0 to T. And then you integrate the left-hand side and use the boundary initial condition. Here, actually, I also have to write, instead of t, maybe I have to write tau. Let's write tau, tau, d tau. And then we integrate over tau. That's a total time derivative. So integrating it, I will get u t0 on the upper integration bound minus u on t0, which we know is 1, identity operator. And here on the right-hand side, if I put h bar to the right, I will get minus I over h bar, integral from t0 up to t, v on tau, u on tau, t0, d tau. So in other words, I obtain for you integral equation. From differential equation, I obtain integral equation, which tells me that u on t0 is defined by the following integral. It's a solution of the following integral equation. That's an important, very important integral equation, to which this operator u on t0 is a solution. And what is important that this integral equation, it actually implements the initial condition. This initial condition sits in this identity operator. And this equation, what is important about it, that it can be now solved by means of iteration procedure. This will produce, the iteration procedure will produce an expansion which produces a solution for this operator u t0 as an expansion in powers of the potential. And typically potential comes multiplied with the Coulomb constant of the theory. So in other words, this expansion in powers of potential will be the same as perturbative expansion in the Coulomb constant of the theory. And how it goes? It goes in the following way. So you say that the potential is proportional to the Coulomb constant. So at first approximation, this is a small correction to the identity. So at first step, you say that u on t0 is simply identity. Once it's identity, you take it and substitute in the first iteration here to the right-hand side, and you get the first correction. So you get u on t0 being equal to 1 minus I over h bar. So first correction will be integral from t0 to t, v on tau, d tau. Yes, u here is replaced by 1. So that's the first correction. So it's not an exact answer, but it's a first iteration. So at leading order in the Coulomb constant, which sits in the potential v, u on t0 is simply 1 minus I over h bar, integral of the potential v on tau, integrated from t0 up to t. Then you take this expression here as the thing which should be now substituted instead of u on tau t0 in this expression, and you obtain the second iteration. So second iteration tells you that the potential will be 1 minus I h bar t0 t v on tau d tau. And now if you substitute it again, you will get contribution at the second order, which reads as follows: integral from t0 to 2t dt1, integral t0 to t1 dt2. So it will be double integral V on T1, V on T2, and so on. And you continue. Now you take this expression here and substitute it back into the interaction term, and you produce triple integral, quadruple integrals, and so on. And so this way is known in mathematics as solving integral equation by means of iterations. Now, at first sight, well, you will get an infinite series provided by these iterations. But this series can be actually massaged in a very nice way, even in a very nice way, and brought to a very elegant form due to the following interesting property. Namely, if you take an integral from T0 up to T1, dt1 integral T0 T1 dt2, V on T1, V on T2, then the integration, which you see here is actually integration up to T, where you integrate over triangle region. So if you draw the coordinate axis corresponding to T1 and T2, then here will be the moment T0, and here T and T. Then our integration region is here. We integrate from T0 up to T1 in the first integral, and then we integrate, so this is T1 running variable, and for a fixed T1, we integrate over T2 from T0 up to T1. So this line here is T1 is equal to T2. So this is our integration region. But instead of integrating this way, so that and that, like this, we can integrate like this and cover the same region, which means that this integral can be written now by changing the order of integration from T0 up to T dt2, integral from T2 up to T1 dt1, and then order, of course, remains of this non-commuting potentials evaluated at T1 and T2 in this way. Now, this expression, in turn, can be written in the following way. So, since the variables T2 and T1 are dummy, these are just integration variables, what I will do, I will change T2 for T1, exchange notations. And then I get the following expression. So from T0 to 2T dt1, integral from T1 to T2. Sorry, here is integration up to T. Here is integration up to T. So therefore, here dt1 and dt2. V on T2, V on T1, where originally the variable T2 was in between T0 and T1, which means that T2 was smaller than T1. Yes, so T2 was smaller than T1 here in the original expression because it runs from T0 up to T1. And when I made this change of variables, T1 for T2, then it turns out that here this T2 variable will be bigger than T1. Because you see in the new setting, T2 is running from T0 up to T. Now, this means that in fact, what I can do with this integral, I can represent it in the following way. So this integration, I can write from T0 up to T dt1 integral T0 to T1 dt2 V on T1 T2. I can write it as 1/2 the same integral from T0 to T dt1 integral T0 to T dt2 V on T1 V on T2 plus another 1/2 where I made this trick of integrating the same region but in a different way. And this gives me integral from T0 to T dt1, integral from T1 to T dt2, V on T2, V on T1. Where in the first integral, we see that that here T2 is less than T1, right? T2 is less than T1. And in the second integral, we see that T2 is bigger than T1. Now, I would be happy to combine these two integrals because the first integral runs from T0 to 2T in dt1, and this is the same in both cases, you see. While in the second case, the second integrals here are complementary. The first one runs from T0 to T1, and this is this one. And the second is running, let's make it maybe with red color to make it visible. This integral here, let's see, where is my red? It's here. This integral here and this integral here are complementary to each other. So the first one runs from T0 to T1 and the second from T1 to T. If I would combine them, I will get just integration from T0 up to T, just like in the first integral. But there is a problem here that these expressions which you integrate are a bit different. They have a different order of potentials. So in one case, this is VT1, VT2, and the other case is VT2, VT1. And in general, these two operators taken at different values of time, they're not supposed to commute with each other. On the other hand, you see that what's happened here is a sort of time ordering. So in the first case, T2 is less than T1, and the younger operator, VT2, is standing on the right. So exactly as time ordered operation does. It takes a product of two operators and puts them in order where younger operator goes to the right. And in the second expression, the situation is the same. Now T2 is bigger than T1, and V on T2 is standing on the left from VT1. So young operator also goes to the right. And this suggests that these two integrals can be now nicely combined in one expression. So 1/2 integral from T0 up to T dt1, integral from T0 to T dt2, So let's write dt1, dt2. And here I have t-ordered product of v on t1, v on t2. So t-ordered product automatically put for me these operators v on t1 and v on t2 in the right order according to the relation, inequality relation between the variables t1 and t2. And this is how this term is nicely written with the help of the t-ordered product. And in fact, if you go on further, then you will see that at each order of perturbation theory, this is in fact 2 divided by factorial, every time you find that at every order of perturbation theory, the result can be represented in terms of integration of a multi-cube region, of which the time-ordered product of the time-ordered product of the potentials V. And therefore, when the boundary of this integration goes to infinity, so t0 goes to minus infinity, t goes to plus infinity, its matrix, which is our operator u on plus infinity minus infinity, takes the following form. It's 1 plus infinite series, n is equal from 1 to infinity, minus I over h bar in the power n divided by n factorial, integral from minus infinity to plus infinity, dt1 and so on, dtn, time-ordered product of the potentials v on t1 and so on, v on tn. And this perturbation theory is called t-ordered product of exponent of the potentials. And compactly, it is written in the following way. You see that what is written down here is, in fact, an expansion of the exponential into its Taylor series. And therefore, it can be written in the following way. T exponent minus I over h bar minus I divided by h bar, integral from minus infinity to plus infinity, dt v on t. Or if you wish to write it as an integration of a variable x0, which is c multiplied by t, then this exponential, t-ordered exponential, is written as minus I over h bar c, integral from minus to plus infinity, dx0 v on x0. So you should understand this expression for S matrix in terms of perturbation theory. You expand this exponential, and then to each term in this exponential, you apply t-ordering product, exactly getting this expression here. Now, transition from quantum mechanics to field theory now occurs in a very simple way. It can be done in a very simple way. We know that in quantum field theory, the potential is given by three-dimensional integral over a local density. This density I denote by IHI, so local Hamiltonian density. Hamiltonian density, meaning that the potential, I mean, this is the interacting part of the Hamiltonian, is given by three-dimensional integral of the local Hamiltonian density. And if we take this expression for our potential and plug it in here, then we will get a four-dimensional integral. And this matrix takes now the following form. That's the following final. That's the following final form, which is used for a practical computation of this quantity. Four-dimensional integral of the local Hamiltonian density time-ordered product of this integral gives S matrix of a quantum field theory. This is how it looks like. One important remark is that reminder that here this Hamiltonian density is time dependent. It's time dependent, and its time dependence is injected by free Hamiltonian. So it evolves according to the free Hamiltonian, injected by Hamiltonian of a free theory, free Hamiltonian. That's the starting point for practical calculations of such a quantity as a S matrix, as we will see a little bit later.